let me, just give the settings for this talk.
Sure.
And I want to thank you, everybody, of course, for attending this afternoon speaker series. And today we have an invited and distinguished speaker. He's Robert Karban, who is currently, I'll try to take your job title right, is CIE Software and System Environment Chief Engineer at the System Engineering Formulation Division, NASA JPL, okay? And of course, I want to have a special thank for Robert for accepting my invitation. So today, Robert will talk about a model-based system engineering approach to model system architecture. So I believe that you are a system engineer or software architecture, this will be relevant to you. So I don't want to take too much time out of Robert, but I just want to say a few words, please bear with me. And actually, I've invited Robert for this speaker series because I came across his recent work on a goal-oriented architecture for telescope control software. It's a recent paper. And it reminded me how similar is the work that Robert is doing with what SKAO is actually doing. Hence, I took this opportunity to give this heads up to everybody. Another reason why I really wanted to invite Robert is because he's constantly pushing, the MBSE, leading all the MBSE effort towards an excellence. And I really feel that, I also have to learn a lot from him. So enough of me now. So Robert, over to you. Thank you.
Okay, thank you very much for the invitation and for the opportunity to share a number of topics in the model-based system engineering world that has been expanding quite and evolving quite substantially over the last few years, I would say. So I'll give an overview. There's a lot of slides. I will not go in all of them in detail, but everything you see today is backed up by one or more papers. You can, I think we'll have the references to that. So you can, if you're interested in one of them, you can look at the papers. So let's get started. So first of all, who am I? We'll keep that short. I'm currently working at JPL as a chief engineer, providing the basically digital infrastructure for model-based system engineering and analysis to our around 4,000 engineers. And my background, most of my life, I've spent with telescopes, mostly optical, a little bit of radio. And also me and my team contributed to a number of missions at JPL, most recently Perseverance, which happily landed on Mars, thanks God. And everything is working perfectly so far, much better than expected. So yeah, you mentioned already the goal-oriented architecture. So that's from a recent paper that we published at the SPIE with my ex-colleague and friend Luigi from ESO. We have been working on that for a while, but has just recently been published. So what are we dealing with today in the telescopes, right? So what everyone knows is that most of them are one-off machines, and there's a substantial amount of emergent behavior, right? You have all these subsystems, and they come together to produce the behavior that is needed to perform the observations. I guess it's the same for the SKA, but I'm talking more here from my experience on the optical side. There's an increasing number of operational modes and control strategies required for with the scale of the next generation telescopes, and they need to be coordinated, and they're often subcontracted, the subsystems that have to be integrated. The lifetime is very long, as you know, and here's just some numbers from the ELT that I know, and other extremely large telescopes like the TMT, that the IO points have increased by an order of magnitude. The actors and sensors have increased by magnitude, and the engineering data that is flowing has also increased. So we're dealing with quite complex systems compared to what was there 20 years ago. Now, due to this scale, we have also an increased risk of component failures because there's a lot of components and they might fail anytime. So the control strategy must be flexible and adaptable to deal with those failures and reconfigure. Well, first detect the failure, isolate and reconfigure the system if necessary to deal with it. The poor human in the loop sometimes is getting overwhelmed more and more by the available information that is on their screens to make the right decision depending on the operational scenario. And there is a lot of interacting and distributed control loops, typically with many connections. When modifications are made, a number of implicit and explicit dependencies have to be considered in the software. So you might turn a little wheel here, which has an effect somewhere else. So which makes it sometimes hard and difficult to tune the individual loops and integrate them end to end. So how we want to tackle that is with a goal-oriented architecture that is based on goals and states. So let me give you an analogy. Everyone, I guess, knows Google Maps, right? So you're driving your car and what you want to do is you have some destinations and deadlines. You need to plan a route. You rely on your gauges and your senses to find your way through on the roads to your destination. So when you use Google Maps, your requirement is to go from a point A to a point B. And then Google plans a route based on your location and the number of constraints. And based on those constraints and some other information like traffic, roadwork, your location, you receive some instructions or directions, goals, as we call them, and to guide you to bring you from A to B. So Google Maps operates in that case what we call in this architecture like a planner. So there's a requirement. It gives you the goals. They are updated and monitored. And you as the driver become the control system and the car becomes the system under control. So these are the basic concepts of a goal-oriented architecture. A requirement, a goal based on the requirement or a number of goals of the requirement, goal planning, monitoring, the control system, and the system under control. Now, you as a driver try to do the best to follow those directions, but sometimes it doesn't work. You miss a turn, and I remember one time, the first time I drove in the UK, and I tried to get out by car from Heathrow, and I was stuck in this roundabout because I could not deal with the reverse side, so it was like 10 minutes going circles. I finally found the exit. So you monitor the environment, right? You look at the traffic light, the other traffic. Google tells you, take the next turn right, and then you try to follow that. So you get a goal, but you as the control system just try to fulfill that goal, right? Based on what we call state variables, so things that change over time, like your speed, your location, the fuel level, and so on. Now, if you fail to achieve such a goal, like turning right, Google Maps will do something, the planner will do something to reschedule. So basically give you new goals to get still to your destination. Now, if you think yourself, you replace the driver with some robot, everything remains the same. What you get are the goals. So what you have to do, but Google doesn't care how it happens. Right? So this is this abstraction of you have some, and what you see here on this picture is this kind of control diamond. So you have the real world, right? So all the things that are going on. You have some goal that is received by the control system, and it tries to achieve it. You have some estimation of your real world, like where you are, how fast you go, and you have some model, and that's of your real world, to use those estimates and perform some control based on the goals. So that's the whole thing about that. Now, how can we use that in the telescope world, and how can we connect it to model-based system engineering? So for some of you, or many of you, this looks familiar. This is a SysML, system engineering modeling language diagram. And what you see here are some requirements, like for pointing and tracking, for dome rotation. So this comes from the optical world. And then you establish some goals, like you want to track on target, but you don't really care how you track on target. That's something, so the goal doesn't specify, it just specifies maybe some parameters, some constraints, but how you actually achieve that is up to the control system. And some scenario, and some people call that the goal network, which consists of a number of goals. Here's only one, but there could be a whole bunch of goals. They can be interconnected depending on each other and so on. Now, with that goal, those goals, we refine what we call procedures. Right? So depending on certain conditions, and here the example is we perform either blind tracking or guided tracking on the target. So a number of environmental conditions, and that's happening on the control system level. So you'll say track on target with certain constraints like the accuracy and so on, and then based on some procedures and some predefined rules, the control system will select what to do, right? What's the best thing to achieve that goal. And we capture all that in a model, right? So we capture the requirements, the goals, the scenarios, and they're all connected. So that's all coming together in the model. But the real driving thing is, for those goals, is what do we want to control? And that's often not so clear. So what in this architecture is introduced are so-called state variables. So these are the things you care about in your system, I mean, system internally, but also externally. And here are some examples. So one state variable is the telescope pointing on sky in altitude and azimuth. But it is affected, and it affects some other things. So for example, the observer position on Earth is affecting that pointing, the rotation, the modeled imperfections of the mount, but it affects also the target wavefront. Right? So this kind of state effects, as it's called, so you identify all the physical states that you care about of the system, but also externally, and determine how they affect each other. Right? And these are the things basically that you have to control when you build your control system. You have to know, and some are you cannot control, of course, like the Earth rotation, but they have an effect on you. So the goals are constraints on those state variables. So when you have a goal, it's associated with some state variables. So I want to have, for example, a goal to point on the sky in certain coordinates. And then from there you say, okay, if I do this, then you also have to take care of true pointing. You have to take care of the azimuth position, of the altitude position, of the imperfections of the telescope, and so on. So you kind of follow all these effects to determine, if you have one goal on one state variable, what else do I have to take care of, right? So to get this picture end to end of control. Now here you see an example of an architecture for a goal-oriented system. You have the telescope, main structure, telescope control system, and so you break down the architecture and you refer those identified state variables. So here you see, for example, the encoder health, the observer's position, the pointing model, and so on. And then for each of those, you have, for each element of that architecture, you have an estimator. So the estimator takes in some measurements that come from your system, right? So like a azimuth position or an encoder reading. And then based on that, you estimate where, for example, the telescope is pointing at the moment. And you that somehow builds up the architecture. And then you have the behavior typically of those components captured in state machines. Here you see a simple example: slowing, tracking, guiding. But also you can incorporate and then model the models of those state variables. For example, here a simple model of the encoder. It's in health, it's in good or bad health. All that together specifies the architectural breakdown, the goals, and the behavior of those components. Now, once you have that, you can, and you build it correctly, you can run simulations and perform analysis. And we'll talk about that a little bit later as well. So here you see an example sequence diagram where those state variables are present, and the TCS. So there's the encoder health and so on. And you see over time in which state they are, in very good, in bad, and so on. The telescope is in idle, slowing, tracking. So what you get is an understanding of how your system should behave, right? The S-design system, which state variables are involved, how they are handled by the control system, and how they change over time. So you can also get some plots of the states over time. Now we have built some prototype some time ago, and what you see here is a UI for goal-oriented operations. So you see the state variables, which are pointing state variable, altitude position, azimuth position, vignetting of the dome is another one, and the goals like track on target, right? And the specification of that goal. Where should it point? What should be the accuracy, and so on. And then you send that to the control system, and the control system, based on that goal, tries to do, based on their strategy, whatever it can to reach that goal, right? And if it fails, the planner executor, like similar with Google Maps, will find a way to reach that goal by issuing new goals. And then you have some plots here. So that architecture, what is important is that with the state effects model, you basically represent the end-to-end knowledge. So you identify deliberately everything that you want to control or need to control, or which affects your control. So you can identify the necessary goals, enable the reconfiguration, rescheduling of the goals to adjust to new situations, but it also enables the end-to-end and tuning. So we also have a separation of concerns from what the control system is, what the system under control is, and that allows us to better design the control system, identifying the measurements, what is estimated, what is controlled. So the state-based pattern that I mentioned before, the control diamond, allows to extend this control system in a consistent and systematic way. Whereas often it happens, you just add things usually, well, maybe not usually, but it's sometimes it's a mix of course of engineering judgment and architecture, but here you have some guidance of how to do that. So I spoke about the executability before simulating it. So what is it about that? So why do we want to have an executable model at system level at all? Why don't we just go ahead and make some diagrams and start implementing? So the main point is to, if you build a model that actually can execute and simulate, is that you increase your understanding of the system before or while it's built. You'll see you can capture the logic, the interaction, the interfaces, and validate the requirements in a system model. Often the requirements come in some shell text, but when you actually try to model them, you will find a lot of gaps and ambiguous statements probably. So it helps you to express the requirements more precisely, but also to analyze how the as-designed system reacts to user interactions, predefined test data, and scenarios. And you can also deal with timing and dynamic resource budget. So you can explore the desirable behavior, but also the things if something goes wrong. Right? So not only the sunny day scenarios, but also inject failures and see how your system will behave at a functional level. You can check the consistency of the design and also understand the roles of the different components, which is sometimes not clear. Who does what, when, right? But it also allows you to use that model to produce other things like documentation, code, simulation, and analysis results. So what we want to do, and we come back here to the goal-based framework, executability. So we want to combine the goal-based framework with executability. Right? So capture all the state values that was mentioned before, identify the goals, but then in order to validate that and eventually validate the requirements, we combine those things. So we produce the system model of the control architecture. We have now an executable set of requirements because we have the goals in combination with the behavior, and therefore can clarify our understanding of the architecture and also of the operations, which is sometimes not so clear. And we can perform various analyses. Now, for executable system models, what are we doing currently? So here are some examples from JPL where we do or have done used executable models. I will talk more about the 30-meter telescope because that's an open source model that everybody can look at. But we used it for basically three different things: to capture things like operation scenarios, fault protection behavior, and flight software behavior. We use activities, state machines, parametrics, and sequence diagrams to capture those. And we produce a number of things from those models: ICDs, functional design documents, and analysis reports, but also code. So on the 30-meter telescope, where I have worked for some time, and JPL has the role of a supplier of a number of subsystems. So there's the TMT organization, and JPL is a supplier in this scenario. And we started with one subsystem, which is the alignment and phasing system, which has a complex behavior and interacts with everything else, and is a key thing to make the telescope work at all. So we started on that subsystem a fully model-based approach. But of course, there is all this other traditional system engineering going on. So in the end, there is a hybrid that uses the advantages of both. We use the MBSE to focusing on, let's say, the behavior, but also the functional interfaces, and to perform analysis and combine it with the traditional system engineering approach. So the objectives there are and were to capture operational behavior, which subsystems are involved in those operational scenarios. Very important, and there's things that came out, is that the interfaces and how the subsystems interact kind of emerges when you capture that. There's a lot of timing requirements that certain operation scenarios have to happen in a certain time. So we captured all those timing requirements, formalized them, and had an executable model with state machines and activities to specify that, and then to analyze if we meet those requirements in terms of time, power, and other error budgets. Using the model, we produced also a number of engineering documents, and we used only standard languages and techniques and off-the-shelf tools. So there was no custom development to enable that. And this is something you get out of that. So that's a sample TMT timeline where you basically see all for a typical scenario, the involved subsystems or components of the as-designed system, the states and the timeline of which component is in which state for which amount of time. Right? So that's for I think that's the scenario for extracting a segment and replacing it and phasing it again. What you see here is basically the overview of the workflow that enables that. We have some requirements that are textual coming from the TMT project office. We capture those requirements in the SysML model. We formalize them in some way so we can actually trace them through the whole model, not only as text but as a formal element. And then we have two designs. One is logical conceptual design, where we basically identify the components, how they interact at the functional level, and which we use then to validate the functional architecture, and realization or implementation model where there's actual boards and translation stages and so on, with in this case used to analyze the power draw of that system. And we perform automated analysis for a number of scenarios to validate if that as-designed system can meet those requirements. And whenever we change something in the design or the requirements change, we go through this workflow and we get a result of, okay, still met, not met. And we produce the engineering documents from that. So we follow a method, which is the executable system engineering method. Basically 5 steps. We identify the boundaries of the mission or the system that we want to build, elaborate the conceptual architecture, capture the component behavior and the characteristics, specify the interactions, and then perform the analysis. So run through this a little bit. So this is like an overview of, we get some specification from the TMT project, we meaning JPL. We elaborate that into some logical architecture, identifying that's the system we have to design. It interacts with a number of other systems that the telescope provides, and we identify those interfaces. And that's an incremental process. So it's not upfront, everything is there, but we capture all those elements, and the architecture evolves driven by the behavior. There's a number of use cases that we model. So we go to the post-segment exchange alignment, off-axis measurements, and so on. And for each of these scenarios, we basically capture the behavior and perform the analysis and see if the as-designed system satisfies those requirements. Now, you see all before the black box level, basically we don't know, we just have the interfaces to the external systems, and internally there is the kind of logical architecture of the individual components. They all have behavior captured using state machines, and they all interact with, okay, the big one here in the middle, which is basically the coordinator of all these others, and interacts also with the external other systems. So this is the alignment and phasing system software, which interacts with the TCS, M1, and other systems to achieve the goal. And all the components are modeled, all the behavior is modeled. So here is an example of the scenario I mentioned before, the post-segment exchange alignment. It's a number of states that you have to go through to align, phase, correct rigid body, and so on. And for each of those, in each of these states, there is some activity that describes what to do. Take an exposure, identify the spots, and then correct the telescope, right? And that sometimes goes 5-6 levels deep. There we capture basically the logic, but also timing constraints. So we can analyze if, when we run through all this scenario, if it meets that specification. Now, since there is not only one component, but many, they also communicate and interact with each other. And that turned out to be extremely valuable, because the combination of capturing the component behavior and interacting them, you actually, and then simulate, you actually execute your interfaces. And I repeat it, you execute your interfaces. And this has been, I think that has been a big benefit. So see, okay, these are the interactions, these are the interfaces, and with the simulation analysis in the executable model, we can actually see how those interfaces, what is necessary as an interface, what runs over the interface, how it is used, how those different components internally but also externally interact. And then you run the analysis that gives you a number of depending on what kind of analysis, number of results. You configure the analysis with certain conditions. You run a timing analysis, a power analysis, and you get some plots, tables, and value profiles that you can integrate into your documentation. Now we have all this beautiful model and the results, and then how do we get it in the document? We don't copy paste it. We actually generate the documentation using something called View Editor and OpenMBEE, and I'll talk about that in a second. So we close the gap between the engineering work and the documentation, where we basically generate the documentation from part of them from the model and combine it with a narrative that the system engineer types up, and we had a live document of the live engineering document that closes that gap between engineering work and documentation that the system engineer always has to do. So what's this enabling technology that allows you to do that? And OpenMBEE is the one that I'll talk about here. So the original, well, just to a reminder, what model-based system engineering claims to do. So it's the formalized application of modeling techniques to support the whole range of system engineering and analysis activities, requirements, design, validation, and so on. Typically use some modeling language and some method that guides you through this maze of things. Now this is an old picture from the early 2000s that I used also many times. The big problem is now we have a bunch of documents, and in the future we only have the model. And I thought that was true, but it's not. Documents won't disappear, in particular for system engineers. That's usually the main deliverable. The main deliverable is a document. But the problem is the disconnect between the document and the engineering work, whatever that engineering work is, right? And it could be a system model. So we thought that a little bit, and what you see here is a model-driven V. So it's the traditional V where you increase, in this case, the requirements, you implement, and then you have the V and V activities on the other side. Now the models tie those together, not only along the legs here, but also across, right? So different sets of models that are integrated and allow you to connect the two legs and also the activities on each leg. So model-based requirements, model-based architecture design, model-based analysis, model-based V and V. That's what we are after. And instead of document driven, so someone writes a document or produces some engineering model, copy pastes in a document the results of some analysis, some hands it over to someone else, and so on. So it goes down this pipeline. As shown here on the left, there's some models, some documentation, some code, some test cases. What we want is to be model driven. So the models are the source of those things, right? So they are consistent. There is consistent documentation. The documentation is consistent in itself with the models, with the code that you might create, the test cases and the analysis. That's what we want. Okay, that's a little bit out of place, that slide. But one other enabling technology is Jupyter. So we have been deploying Jupyter at JPL in many places now. And Jupyter is basically a notebook where you can combine code, scripts, and text, right? And it's used for engineering, data science, scientific computing, and many other things. But for us, it has become like a hub for model-based system engineering, because we can integrate whatever we have we have our models in certain repositories. People write their notebooks and actually access data from the models, use it in their analysis or in their engineering work, push back results to those models or updates, and therefore close the loop. So there's not anymore this world of, okay, there's one SysML tool and that's the only place where I do it. No, there's a whole range of things in this environment, in this model-based engineering environment, and Jupyter plays an increasing part in this environment and enables people to use model and engineering data in a very easy way in their daily work. We'll not go through that, and we use that, for example, on the rover. So Jupyter was used to build the test procedures and for the robotic arm, where we have the whole test procedure captured in a Jupyter notebook with sign-offs and so on, and basically run through that, can automate it and so on, and it can be connected with various model-based repositories if needed. The OpenMBE environment, which is at the core of this, so we have the language, SysML, we have architectures, but in the end, all this only works if there is an engineering environment that supports you in your activities. It doesn't help if you have wonderful models, but then it's stuck in some tool. So over the last 5-6 years, this community has formed. So OpenMBE is a community for open source modeling software and models. And it has been growing quite a bit. We have currently more than 400 members from different organizations across industry, from aerospace to automotive, all having the same goal: building a model-based engineering environment that enables to perform system engineering tasks, system engineering analysis tasks in a model-driven, model-based way, providing some core software, but also people contribute models to that community that can be shared and reused. Which brings me to the engineering document section with OpenMBE. So the main task of system engineers to guide the concurrent collaborative design of a complex technical system, right? So this interdisciplinary work, which involves usually a lot of people. What you see here is the team, the product team for perseverance, and they are becoming really large, right? And there's a lot of communication and a lot of interaction, and they often start very small, right? Someone produces, in our case also JPL, we have a lot of Excel-driven system engineering. documents, PowerPoint, right? So you start simple, people iterate on their models, enter the data into the rollups for mass, for example, get inputs from others. So this the increasing network of documents, Excel sheets, PowerPoints, and so on, can get complicated very quickly, right? And then you have this guy here in the middle, the meeple, as it's apparently called, and is kind of lost. Where is the latest information of that I need? What is up to date, right? How do I find that? And so here is some kind of abstracted quote from from our engineers that I enter data all day long, but I want to do some real engineering, right? And I'm not the janitor. I'm a system engineer. So there is this kind of ratio of overhead to between like repetitive data entry, the version confusion, what is the right thing, and the constant searching for information, right? So, but what we want to do is novel engineering work. We don't want to spend most of our time doing those things, right? So all projects will benefit from minimizing that overhead and favor it for novel engineering. So what is proposed, instead of having this maze of things where we have all these implicit dependencies and different versions, to kind of organize that, right? And shift away from email and manual data management to some authoritative single source, which is kind of unified, right? To connect the information between those documents and the engineering work, right? So not to have this implicit thing, but actually connect those. So the information is referring to some authoritative source of truth. And that brings us to the kind of, say, paradigm of OpenMBE, right? Of the community, but also of the engineering environment that we want to build. We have some model, we have some documentation, we have some relations, but this information is the same, right? And we don't want to copy paste this thing here over here. We want to update it once and then use everywhere, right? And this is the driving vision of OpenMBE and everything that is built around. So there are different things that are in this OpenMBE open source software and models repository that is produced by the contributing members. There is the model management system, which basically enables you to capture the model, but also from different sources. So there's not only one single repository. There's of course many, but the MMS is somehow the enabling those connections and across those models. The view editor, which is the web application that allows you to author engineering documents referencing engineering data. And so when the engineering data or model is updated, the document also updates, and you don't have to copy paste and take care of that. It will be version controlled, configuration managed, what we call cross-referencing data, which is captured in the MMS. And whatever is needed you want to have from other repositories, you would kind of have bring over here and then build your engineering documentation. There's a number of model development kits, as we call it, which is basically the different integrations with a number of tools to populate that MMS. And one of them, the most famous one, is probably the one with Cameo, SysML modeling tool, or Magic Draw, whenever you change the system model, it will get updated here, and you can use all that information in View Editor. There's Meanwhile, quite some documentation and training, videos, and so on. And there is the 30-meter telescope model, which is also part of this open source repository, along with a cookbook. And the cookbook captures all the patterns, practices to build a system model and a system architecture, which emerge from the effort on the 30-meter telescope work. So so we'll see here somehow the three parts here. So we have the MDKs, the model development kits, which are connected to your engineering modeling side. They will update the information in the authoritative source, which is the MMS, and then you use that information to build your engineering models and author your documents. I'll show one example here, one very simple example where a flight system engineer interacts with the MMS without knowing, building the MEL, the master equipment list, and a subject matter expert who has to produce the documentation. So I have a little video here, and I hope that works. Sometimes it doesn't. Let's see if we can get that, or I get the usual error sometimes. Otherwise I switch. Oops, sorry. Go here. Yeah. Okay, the usual thing. Okay, 1 second. Yeah. How can I get out of this? So, here we go. Let's do this. That should work. Okay, here we go. So what we see here is, play this. So what we see here, so this is view editor, and it's based on the ISO 42010 paradigm of view and viewpoint. So basically you create a view for a certain stakeholder concern. In this case, it's the master equipment list. And all those things that you see on this page, all the things that have like this little wire frame around it, are actual references to the engineering model. Right? So whenever the model changes or you change it here, that's why it's called editor, it will keep both in sync, and you can build your document like this. So what we'll see here in this example is that we're gonna change the name of one of the components, and this actually refers, as soon as we hit save, in this case the SysML model will be updated. We update some values like the mass, and then another person uses Excel to do a mass rollup, for example. So here's the previous version. That person now updates the model and gets the new values that have been changed on the document side. So two different roles referring to the same authoritative source of truth. Now this person adds another component here by just simply adding a new line in that Excel sheet with analysis analytic instrument 4 with some mass, commits it back to the model. And on this side here you see there are 3, and once that is updated, we get reflected the change of the model. So basically this shows you how the the interaction between different end user tools or applications interact on the same model, producing documentation, but also performing analysis. Now, over the last few years, there has been an increasing number of adopters and contributors. So here you see all the projects that we have, where we have used OpenMBE at NASA JPL, other science and engineering institutes that use the SIM system, but also industry has adopted it. So Boeing in particular at the forefront, together with Ford and Lockheed. But also the standardization efforts have started to use the OpenMBE system to handle the complexity, and an increasing number of vendors have built integrations with that open source environment. Here's an example of the very first application at JPL with Clipper, where we had about 100 users, produced more than 230 documents, but the important number is here, is this 445,000 connections between elements. So the maze I showed you before, these implicit connections are now explicit. And that's a huge number. This means that all the documents that you had built before manually are actually now consistent with the engineering model and among themselves. And we have made those connections version controls, configuration managed, and explicit. So we know about them. The Mars 2020, aka Perseverance, used OpenMBE and associated environment to produce a number of documents like the reference designator list, electrical function list, and block diagrams. And here the emphasis was more on the technical rigor and detailed modeling and communication of system and subsystems, right? To be capable of a high fidelity connection tracking. So we had about 50 concurrent users, 90 plus documents, and 180,000 connections. But does it scale? And Boeing demonstrates that it scales. So Boeing commercial airplanes has deployed it at corporate level, has around 1,000 concurrent users across 50 programs, and Lockheed has around 100 users and 50 projects. So the scalability of that many people can use this authoritative source of truth, contribute it, use it, modify it, and collaborate through it has been proven by those aerospace industry contributors and adopters. The next step that we took was driven by Stevens as part of NavAir model-based acquisition strategy. So they wanted to show how can we interact between organizations in a model-based way, exchanging models, working on those things. So they built a pilot project that was delivered to NavAir, which is the Navy, and also using OpenMBE and View Editor to sign off, perform digital sign-offs on documents, push them back to the model, and having in that way collaborating between different persons and roles on the same model using generated documentation. So today we have an environment in place, in production, which is within the organization. What you see here is some buildings at the JPL lab, which I've not seen for a year now. But we are using OpenMBE to connect those different engineering models and documents that we need to produce. What we start to do is to move from the inter-organization to an inter-organization concept with the next project, which is Mars Sample Return, where we go not only within JPL, but expand that to Marshall and to ESA and see how we can work across organizations in a model-based way. And we are moving gradually there. by exchanging models, collaborating on same engineering work and documentation. And the final vision is this global engineering ecosystem, right, where we have connected engineering information across organizations, working on some mission. That's the mission and the vision that we have. Okay, thank you very much. I think I'm almost on time.
All right, thank you very so much. I really enjoyed your talk, your presentation. I'm just conscious about the time, and people are actually disappearing in 4 minutes. Okay, so there are a couple of questions in the chat. If you don't mind, if you open the chat, there's Kwande asking a couple of questions, and then you know, if people are disappearing at 4 o'clock sharp.
Yes,
please,
of course.
Thank you.
Okay, let's see what we have.
No pressure, Robert, no pressure.
No, it's fine.
Time is always a tricky resource.
Okay, so code and the model. Yeah. So the question is, how do you see real code in terms of the identity between code and model? If you have well-documented code, does it better represent your model, or would you still rather have a system engineer artifact instead of the code? I think what we have practiced, and I've practiced that for telescope control software back at ESO, and we are establishing also that at JPL now, is that in the end, the code and the model become the same thing. So you have a model, in particular if you have an executable model with specified semantics, you generate your code, and there are different levels and granularity that you can do. But when you update the code, update the model, you also update the code. So the barrier between those really becomes very, very blurry. So there is established frameworks to enable that, where you model, simulate, model check, validate, generate the code, and go from there. This pipeline is well established. There is also a number of papers which are available. What is the development process model for OpenMBE? So I'm not sure if you talk about the infrastructure itself or how it's used.
No, it's mostly, for instance, how do you do the vision, and how do you make sure that you have people working on things, and how you steer the development process?
You mean of a system using OpenMBE or OpenMBE itself?
For OpenMBE itself.
Okay, so it's an open source community. There are some main contributors. We have regular meetings where we tag up architectural meetings, but also community meetings, and also leadership meetings. You are welcome to join any of those. And there we decide basically, okay, what's the roadmap? What are the features we want to implement? And it's community driven, right? So the needs are coming, like Boeing, us, Lockheed, right? And we decide together where we spend our efforts, right, to evolve that system. So it's completely open and transparent. You can join anytime and participate, contribute, or just listen in.
Thank you.
How about round-trip engineering, code of models? How do you come with manually generated code? Yeah, I think I've spent a lot of time. I started code generating almost back in the 90s. And my conclusion is the round-trip thing never really worked well. I mean, it didn't work 20 years ago, and still today, there's always hiccups. So the recommendations, and there's also some papers where we talk about this, is really only a one-way thing and integrated along the pipeline. There's a model, you produce something, and you inject manually crafted code where necessary. So there is I think a division of what you want and can do in a model, and what you want to really do on the development side. If you try to do either in both, or everything in either of them, I think it's not going to work. So it's better to focus on what you can do in the model and restrict it there, and then generate code like the logic of a state machine, and then combine it with handcrafted code. Round trip, I'm not a big fan of round trip. Has Boeing expanded OpenMBEE to function with their, I don't know. But I think that's something you can ask if you join so there's a specific question about Boeing. I think you can ask that on the Slack or Google Groups OpenMBEE channel. Boeing people are present there, so I don't know. Another question, in my early experience in industrial automation automotive, we often use development and validation process that used to go from modeling loop to software loop to hardware in the loop before the final system. Yes, so the model-based engineering environment is that whole scheme. So it's not only SysML or whatever. We want to have that rich set of features in this environment to enable all these things, software in the loop, hardware in the loop, and so on. And there are so we have done that. So we have, for example, have a SysML model that had the logic and ran it with hardware in the loop, where it drives basically the simulation is integrated with the hardware or software in the loop, and can also be combined with Simulink. So the idea is to have that rich environment to allow those integrations and that support for analysis. I think that was the last question, and it's 2 minutes.
Robert, there is another virtual hand up. Is it Rob? Rob?
Yeah, I think my question is, particularly relating to the SKA, there's a lot of heritage behind the development and the documentation and all the requirements. I mean, we're on the 12, almost 13th iterations of system requirements already. How do you go about starting this sort of process when the project is already quite far along in its development?
Very good question. Excellent question. So I think that we call that process model hardening. I mean, even if you start from scratch, a new project, and I did that mistake very early on in my model MBSE career, try to capture everything in a model and try to formalize it, but it doesn't work. You will never finish, right? You will never produce anything, right? Because you do only modeling, and the added value is not always clear. What is important is that gradually it can become a model, but the view editor approach allows you to do that. So the view editor is connected with the model, and everything you see in the web app actually goes into the model repository, and if it's only text. So the first step is just to take that text wall, put it into view editor, and now it's in the model, and you can connect it to the model if it is only text. And gradually you would increase your let's say MBSE formalism, say, okay, this actually I need to investigate more, and it's worthwhile to build a model. So you build a model for a part, and then in your text or in your document, you start cross-referencing those engineering models. And let's say in the beginning, you might have of the product, or if you import these things, you might have only text. But as you go along, you will see more and more cross-reference. So if you have certain components or concepts that is only text in the beginning, you will have in the end more and more of those wireframes that actually reference a particular model. So this is always, I mean, in any case, if you start in the middle or the beginning, it's not very clear sometimes. You can start with some structure, of course, but I think this model hardening process is very important. You start informally, but it's there, accessible, version controlled, and can be connected and elaborated over time if needed, right? Because not always it's needed. It's enough maybe to just have the text, and for some you add the model and then elaborate that. Does that answer your question?
Yeah, thank you.
Any more questions? Okay, so if not, can I ask you please to unmute yourself so we can give a round of applause to Robert? Please. This is our virtual way to thank you, Robert.
Thank you very much.
And if I may conclude this saying that you essentially confirmed that, the similarities of the work you're doing at JPL and your previous experience, of course, with what also SKA is trying to do in not only in the control system, but also there's an aspiration for the system engineer to take on the model-based system engineering once again. So I think that we can conclude almost on time this presentation. Thank you, everybody.
Okay. Yeah, thank you very much for having me.